All right, today we're going to pull back the curtain on a concept that, believe it or not, secretly runs so much of our modern world: vector spaces. Now, I know that sounds super intimidating, but it's actually a beautifully simple and powerful idea. And trust me, by the end of this, you'll see exactly how. So let's kick things off with a little puzzle. What's the hidden thread connecting the amazing graphics in your favorite video game, the way your phone processes sound, and the AI that just recommended your next movie? Stick around, because the answer, well, it's at the very heart of what we're talking about today. To make this all feel really intuitive, we're going to start in a playground. But this isn't a playground with swings and slides. Nope. Our playground is that simple XY grid you definitely remember from math class. It is the absolute perfect place to start getting a feel for what a vector space really is. So, what's in this playground? Just one thing: vectors. And for now, you can just think of them as arrows pointing from the very center, the origin, out to any other point on the plane. Every single point on this grid has an arrow that points to it. Now, every good playground has some rules, and rule number 1 is all about addition. If you take any 2 arrows in our playground and add them together, placing them tip to tail, the new arrow you make has to land somewhere inside the playground too. You can't just add 2 vectors and suddenly find yourself outside the 2D plane. It's self-contained. And rule number 2? It's about scaling. You can take any arrow and stretch it out, shrink it down, or even flip its direction completely, just by multiplying it by a number, what mathematicians call a scalar. And no matter how you scale it, that new arrow you get still points to a spot inside our original playground. It always stays in the plane. And that's it. Seriously, those are the only 2 rules you need. Okay, so we've been messing around with these 2 simple ideas in our little 2D world. So now, let's bridge the gap and see how these intuitive playground rules are actually the official mathematical definition of a vector space. And here you have it. A vector space is really just a collection of vectors that's self-contained, or to use the fancy math term, closed, under addition and scaling. All that means is when you do those 2 things, you never leave the space. What happens in the playground stays in the playground. So here's the bottom line. If you want to check if something is a vector space, you really only need to ask 3 things. 1, is it closed under addition? 2, is it closed under scalar multiplication? And 3, does it include the origin, that 0 vector, which is kind of our home base? If you can say yes to all 3, boom, you've got yourself a vector space. Okay, now for the really cool part. You might be thinking, this is all just about arrows and grids, right? But the true power of a vector space is that it's an abstract idea. So let's take a quick tour through a whole zoo of other things that, surprisingly, are also vector spaces. First up in our zoo, polynomials. So get this, if you take all the polynomials up to, say, degree 2, that entire collection forms a vector space. Why? Well, think about it. If you add 2 of those polynomials together, you get another polynomial that's degree 2 or less. And if you scale 1, same thing. It totally obeys the rules. What about something like square matrices? Yep, those too. Add any 2 3x3 matrices and you get another 3x3 matrix. Scale 1, and it's still a 3x3 matrix. And of course, there's a 0 matrix. So yeah, the set of all square matrices of a given size is totally a vector space. And this is where things just get kind of wild. I mean, look at this list. The set of all real numbers, that's a vector space. Specific kinds of matrices, like symmetric ones, you bet. Even the collection of all possible continuous functions, that's a vector space too. This same fundamental structure just keeps popping up everywhere. Okay, so now that we've got a handle on what a vector space is, let's take it a step further. We're going to go back to our friendly 2D plane and see if we can find smaller, self-contained playgrounds hiding inside of it. And this brings us to the idea of a subspace. And this visual just lays it out perfectly. On the left, that's our big playground, the whole 2D plane. But look at the right, a single straight line that goes right through the origin. That's a perfect example of a subspace. It's a little world living inside the bigger one. This right here, this is the key insight from the source material. Geometrically speaking, any straight line that cuts through the origin is, all by itself, a complete vector space. It's not just some line, it's its own self-contained system. Just think about it, right? If you take any 2 arrows that live on that line and add them, their sum is going to be on that same exact line. If you stretch or shrink any vector on that line, guess what? It stays on the line. It follows all the same rules of our big playground, just in a more restricted, one-dimensional way. It's a mini playground. And that's really all the formal definition is saying. A subspace is just a chunk of a bigger vector space that happens to satisfy those same three core properties all on its own. It's a vector space living inside another vector space. Simple as that. Now, it turns out that for any vector space you can think of, there are always at least two trivial or kind of obvious subspaces. The first one is the entire space itself, which, yeah, makes sense. The second one is the smallest possible subspace, just the origin, the zero vector all by itself. It might seem a little boring, but it perfectly follows all the rules. So, why on earth did we just spend all this time talking about lines inside of planes? Why does any of this abstract stuff actually matter? Well, it matters because finding these simpler subspaces is one of the most powerful tools we have for making sense of huge, complex data sets. Okay, imagine every movie you've ever watched is a single point in some massive, thousand-dimensional vector space. I mean, you can't even picture that, right? It's chaos. The idea of a subspace lets a machine learning model find a simpler plane or line hiding within that chaos, a subspace that might represent, say, the entire action movie genre. It's how we find simple patterns in overwhelming complexity. And this leads us to a really crucial question. If we have just a few building block vectors, can we combine them through adding and scaling to create every other vector in the entire space? This one question opens the door to huge ideas like linear combinations and basis vectors, which are like the true alphabet of any vector space. And here's the next big puzzle. If we want to rotate or stretch this entire playground, we can't possibly move every single vector one by one. There are infinitely many. So what's the secret? How do we transform the whole space all at once, efficiently? The answer is the key to all computer graphics. You see, answering those two big questions is the whole foundation of linear algebra. It's how we build 3D graphics engines, it's how we compress massive files down to a manageable size, and it's how AI models learn to find the signal in the noise. And it all starts with the simple rules of our little vector space playground. Which, of course, brings us all the way back to where we started. 3D graphics, audio signals, and the incredibly complex data that AI models train on, they can all be represented as vectors. And the ways we manipulate them, combine them, and analyze them are all governed by the simple, powerful rules of the vector space they live in. It really is the secret language of data.